Welcome to a series on videos on working with derivatives. Once we could use the derivative rules to help us find derivatives fairly quickly and easily, now we can actually start applying those derivatives to multiple situations. The first that we're going to talk about in this video is applying derivatives to following objects. Don't forget to like and subscribe, and let's get diving right into this problem. So hopefully somewhere along your math careers you were told about following objects. When an object is either thrown or dropped from an initial height, the object will travel in a parabolic trajectory. The height of the object h after t seconds can be modeled with the following formula. H equals negative 1/2 gt squared minus v sub 0 times t plus h sub 0. Now let's talk about this real quick. First, I hope everybody knows if you throw a baseball, throw a rock, it's going to travel in a pattern that looks like this. This equation is going to tell you the height of that object at any given time in seconds. So the main variables in this problem are, of course, h. That's the height of the object after t seconds. So there's my t, and there's another t right there. But there's a couple other variables in this problem that are constants. They're going to be changed to numbers for a specific problem. The first is the g. G is the acceleration due to gravity on Earth. Now, the acceleration due to gravity depends if you're in feet or meters. You got to make sure you read the problem. So if the problem is measured in feet, you could change that g to a 32. Negative 1/2 times 32 will make that a negative 16 as my leading coefficient in front of the t squared. If it's 9.8, because my problem is measured in meters, I'm going to replace that g with 9.8. Negative 1/2 times 9.8 is negative 4.9, so my leading coefficient would be negative 4.9 t squared. So that g will get replaced in a specific problem. The next variable here is this v sub 0. That is the initial velocity of the object. If the object is just dropped, that would be a 0. There would be no initial velocity, just dropped, and then acceleration due to gravity picks up. But if you throw an object, or you throw a rock, you throw a baseball, you are putting some type of initial thrust or initial velocity onto that object, so there will be initial velocities there. And I apologize, I just realized this should be a plus sign right there. Sorry for that. Now, the h sub 0 right here, that is your initial height of the object. So if you're throwing the baseball from your hand, maybe your hand is 4 feet above the ground, or if you're dropping a rock from the top of a building, maybe that building is 200 feet tall. So that h at the very end is going to be replaced with the initial height of the object that'll be given in the problem. Now, let's make sure that we read the problem to know the units. That is really, really important because, again, it all comes down to feet or meters, and that determines your g value. So if your height is in feet, then your gravity due to acceleration, or your acceleration due to gravity, excuse me, is that 32. So when we plug 32 in for g, multiply it by negative 1/2, we get that negative 16 as my leading coefficient. If that g value is 9.8 because I am in meters, then when I plug 9.8 in, multiply it by 1/2, I get the negative 4.9 that we see right there as my leading coefficient. And again, the initial velocity and initial height are also going to be given, and I apologize again, these should be plus signs. Don't know what happened there. Okay, so let's just talk a little bit more here about how we're going to connect this to derivatives. So as that object travels, we could think about its velocity, speed with direction. So speed is always a positive number. When you throw a negative in front of it because it's going in a downward movement or a downward trajectory, then that now is velocity. So velocity is simply speed with direction, either a minus sign or a plus sign. Now there are two types of velocities. Now keep in mind, velocity is measured in distance per time, feet per second, meters per second, whatever. So there are two types of velocities. The average velocity between 2 points. So we have 2 points, 1 point here, 1 point here. What's the average velocity between them? The second type of velocity that we have is the instantaneous velocity at a single point. Now, velocity again is either going to be feet per second or meters per second. And boy, another typo. I'm so sorry. Either, not weither. I don't even know what I'm trying to say there. All right, so let's talk a little bit more about average velocity. How do you find average velocity? Well, again, average velocity is the velocity between 2 points. So first, I need 2 points. So my points are t, comma, h. I have a time, and that time produces a height of the object, and I got 2 of those. So I got my first point, time 1, comma, height 1. I got my second point, time 2, comma, height 2. So to find the average velocity between these 2 points, we're simply going to use the old algebraic idea of change of y over change of x. But in this case, it's going to be change of height over change of time. So we're going to subtract our heights as my numerator, that is my y values, my output values, over subtracting my x's, or my times, that's my independent variable, in the denominator. So again, remember, distance is feet per second, or meters per second. So the numerator is going to be your difference in your distances, your heights, and then the denominator is going to be the difference in your time. So you're going to end up with that velocity, that average velocity that's going to be measured in either feet per second or meters per second. So very, very simple to find average velocity, not difficult at all. But here is where we're going to connect derivatives. Instantaneous velocity is how fast that object is traveling at a single point. Well, to do that, we need the derivative. So the derivative of the height function is the formula for the instantaneous velocity at any given time t. So if you're asked to find the instantaneous velocity at a single point, you cannot use out-of-school algebra, because out-of-school algebra requires 2 points, but you can use the derivative. So let's talk about the derivatives of these two values. So in feet, here is my height function. And if I take the derivative using the power rule, the 2 falls down in front. It joins the constant multiplier, negative 16. Negative 16 times 2 is negative 32t. My new power is just a 1 right there. And using the sum and difference formulas, again, there should be a plus sign. I'm so sorry for that typo. I feel terrible. But again, the initial velocity is just a constant. So when we find the derivative of t is just 1, because again, the 1 falls down in front. 1 times the initial velocity is the initial velocity. And then my new power on the t becomes a 0, but anything raised to 0 is 1. And then finally, the derivative of the constant in the back, the h sub 0 is just your initial height. That's just a constant number. And we all know the derivative of a constant is 0, so that's gone. So again, we have a formula for the velocity, which is the derivative of our height function. It is negative 32t plus the initial velocity. Now, if we're measuring this in meters, once again, the only change is we have a negative 4.9 as my leading coefficient. And I'm once again going to take the derivative. So the 2 falls down in front, multiplies in front. And oh my gosh, I didn't do the multiplication. What's wrong with me? Boy, I feel really bad. I was slightly poorly planned here. I apologize. Let's fix this. The 2 falls down in front. We get negative 9.8 t to the first plus v sub 0. That's my constant initial velocity. Once again, make sure you understand why it's just v sub 0, because the 1 that is on the t is going to fall down. 1 times v is v. And then my new power on the t is 0. T to the 0 is just 1. And then again, the h at the end is my initial height. That's a constant. The derivative of a constant is 0. So the velocity formula, if you're measured in meters, would be negative 9.8 t plus the initial velocity. All right, so again, hopefully that makes sense. Pretty easy, right? We've learned enough about derivatives to understand that a derivative is the instantaneous rate of change, in this case velocity, at any given time. All right, let's use all this to actually explore some problems. So the first problem is this. A baseball is thrown off the top of a 100-foot building with an initial velocity of 85 feet per second. Couple questions here. Create the function for the height of the ball after t seconds. Okay, this is easy. I'm just going to use my formula. So the height of the ball after t seconds is going to be, okay, well, now I measured in feet. The initial height was in feet. The initial velocity was in feet. So I'm definitely going to use the negative 32 here. Negative 32 times the 1/2 t squared plus the initial velocity, which was the 85 t, plus the initial height, which is 100. And then again, as I discussed, most students actually skip this step. But when we take that negative 32 times the 1/2, we're just going to get a negative 16 there. So negative 16 t squared plus 85 t plus 100 is my formula that can find the height after any given time t. All right, so the first question here is an average velocity question. It says find the average velocity of the ball over the time interval 1 to 1.6 seconds. So basically I have to figure out what is the height at a time of 1 second, what is the height at a time of 1.6 seconds. So I'm going to get my heights. So again, all I have to do is plug 1 into my height formula. And if I do that, grab a calculator if you need to, unless you can do it in your head. But I get a height of 169 feet. So after 1 second, the ball is 169 feet above the ground. And then I'm going to plug 1.6 in, and if I plug 1.6 in, the height of the ball at 1.6 seconds is 195.04 feet. So I have my 2 points. At point 1, my height is 169. At point 1.6, my height is 195.04. So to find the average velocity, I'm simply going to subtract my heights on top, 195.04 minus 169. And then I'm going to subtract my times on the bottom, 1.6 minus 1. So on top, that's a difference of 26.04 feet. So that's how far the ball has traveled in that 0.6 seconds. 1.6 minus 1 is 0.6 seconds. So the ball has traveled 26.04 feet in 0.6 seconds. So dividing that, that gets me an average of 43.4 feet per second. So from the point 1 to point 2, the ball has an average velocity of 43.4 feet per second. Average velocity is pretty easy, does not involve derivatives at all. All right, but what about the instantaneous velocity at 1.1 seconds? For this, I'm going to need the derivative. So again, the derivative is pretty easy to find. It's simply taking that power of 2, dropping it down in front, which is going to create a negative 32t, plus the initial velocity of 85. Pretty simple there. I'm just using the constant multiplier, the power rule, and I'm using the sum and difference rules there to find that derivative. So the derivative of the height is our velocity formula here. So now all I have to do to find the instantaneous velocity at 1.1 seconds is literally plug 1.1 into the derivative or the velocity function. Pretty easy to do here, not overly difficult. So grab a calculator if you need to, but you should be getting 49.8 feet per second. So if I pause time at 1.1 seconds, the object, the baseball, was traveling at 49.8 feet per second. All right, what about the 2.9 second mark? What's the instantaneous velocity at 2.9 seconds? So I'm going to take that negative 32, multiply it by 2.9, add the 85, grab a calculator please, but we get negative 7.8 feet per second. Now let's talk about the fact that the first answer was positive and the second answer was negative. What's up with that? Well, when an object has a velocity that's positive, it means it's on its way up. So at 1.1 seconds, the baseball must have still been on an upward movement, going up. But at 2.9 seconds, it must now be coming down because the velocity is negative 7.8, and negative velocity means that the object is on its way down. Makes a lot of sense. All right, last question here for this particular problem is, what is the instantaneous velocity at the max height of the ball? So when the ball is all the way at the very top, how fast is it traveling? Well, the first thing I got to figure out is the time, right? Because my velocity formula is based on time. I need to plug a time into it. So at what time is my baseball at its maximum height? Well, for this, we have to remember our vertex formula. Remember, this is a parabola. My original function measures the height of the ball after t seconds. That's a parabola. And to find the vertex of a parabola, it's, hopefully you remember this formula, negative b over 2a. That tells you the x value, in this case, the t value, because we're using time as my independent variable. So if I simply use negative b over 2a, I can get what the time when the ball reaches the max height is. So negative b over 2a. Now I'm not using my derivative here. I'm going all the way back to my height function. That's going to be negative 85 over twice a, which is negative 32. Negative 85 divided by negative 32 is 2.65625. So that means that I just figured out that at a time of 2.65625 seconds, the ball is at its very peak. So now, to find the velocity at that time, when it's at the max height, all I have to do is plug in that time to my velocity function, which is, again, the derivative of the height function. So negative 32 times 2.65625 plus 85. Grab a calculator and you get a velocity of 0 feet per second. Now, we might say, what? 0? This actually should make complete sense. Because when that ball reaches its maximum height, Gravity has now equaled the initial thrust, and the object is basically paused. It's like just sitting there, and then gravity takes over and the ball comes back down. So at that maximum height, it actually makes complete sense why the instantaneous velocity is 0. Because when that object is thrown, it has that initial velocity on it that's causing it to go up, 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 even though gravity is pushing down on it. Eventually, gravity wins out, and that object is just at the very, very tip top, where it technically has a velocity of 0, and then gravity kicks in and brings that ball back down. So it makes complete sense that even though we did all the math, it makes sense I actually didn't need to. I should understand that the very peak of that height formula, the instantaneous velocity is 0. All right, let's do one more problem here, a little bit different and a really good ending problem here. So a diver jumps from a platform that is 32 feet above the water with an initial velocity of 16 feet per second. Create a function for the height of the diver after t seconds. So our formula, again, remember, is -1/2 times g. I'm clearly in feet here, so that would be -1/2 times 32, which is going to be a -16 t squared, plus the initial velocity of 16 times t, plus the initial height of 32. Okay, great. All makes sense. Now, I want to just pause real quick to mention that I was constantly, if we go all the way back here, I was changing that minus sign to a plus sign. I had that wrong. But I want to make sure it's known that you could put a negative initial velocity onto an object if you were whipping an object down because you're throwing it down, then that would be an initial velocity that could end up being negative. But if you're a diver, you're jumping up off that platform, your initial velocity is going to be positive because your initial movement is going up. Same with that baseball. So I don't want to take away the fact that the initial velocity could possibly in some situations be negative. But if you're throwing something up or you're jumping up, your initial velocity will be, of course, positive. All right, so the first question says, at what time does the diver hit the water? Okay, so here is the platform, here is the water. Diver jumps up into the air and comes back down and splashes into the water. So what time does the diver hit the water? Well, let's think about that for a second. When you hit the water, your height above the water is 0. So if we take our height function and set the height as 0, we could then solve to find the time, t, that creates a height of 0. And if the height of the diver is 0, that diver has hit the water. So this is actually an algebra problem. It's nothing to do with derivatives yet. So let's see here. A couple different ways to solve a quadratic. You got the quadratic formula. You complete the square. You could factor. You could even use a calculator. But I'm going to go ahead and factor this. I'm going to factor out a -16. So I get t squared minus t minus 2. Check my factoring if you don't believe me there, but I believe my factoring is correct. And then I can continue to factor that trinomial. That's going to be t plus 1 and t minus 2. Check my math, but that should be a pretty good factoring job, which means that there are two results for t, either -1 or +2. Now, the first value of -1, I'm going to cross out, because when you're working with time, it always goes up. Time cannot be negative. So if I'm this diver and I'm going to start at the top of that platform and then hit a stopwatch, the time only goes up. It cannot go backwards. So a negative time wouldn't make sense in this context. Therefore, the time it takes for the diver to hit the water is 2 seconds. So this entire process of jumping up into the air and coming all the way back down and splashing into the water takes 2 seconds. All right, the final question says, what is the diver's velocity at impact with the water? So what we're asking now is, when that diver smashes into the water, what was his or her instantaneous velocity? All right, now we already know the time to hit the water is 2 seconds. All we have to do is plug that into the velocity formula. Well, what's the velocity formula? Well, the derivative of the height formula. So if we go all the way back to our height formula, this 2 is going to fall down in front, make that a -32t plus 16, because our new power on this t would become a 0. Anything to the 0 is 1. The derivative of a constant 32 is just going to be 0. So my velocity formula is going to be -32t plus the initial velocity of 16. There it is, not too difficult. So now all I have to do is plug in 2 seconds to get my instantaneous velocity when the object hits the ground. -32 times 2 plus 16 is -48 feet per second. Makes complete sense because obviously when the diver hits the water, the diver's on his or her way down. So that means when they splash into the water, they better have a negative velocity because again, velocity is speed with direction. And when they hit that water, they had a velocity of negative 48 feet per second. All I had to do was find the time it takes to hit the water, doing a little bit of solving there. And then I had to actually plug 2 into the velocity formula, which is again, just the derivative of the height formula. All right, that's it for this video. So the key thing is making sure you remember the height of a falling object model based on t seconds. And then the derivative of that formula is the velocity of that object at any given time t. Pretty simple, pretty easy way to utilize derivatives. Hope you liked it. Talk to you later.